Hello again, my dear students. Now with our first lecture after the Christmas break. So Merry Christmas and Happy New Year. And let's now return back to our module with chapter number 6, dealing with our third device in this module, which is the bipolar junction transistor. So please permit me now to start sharing my presentation and start this short journey. So one lecture, one device journey with the bipolar junction transistor. Okay, I think you can now see my shared screen. Let's also operate my my pointer. Okay, I believe now everything is working properly. So let's start our lecture with the bipolar junction transistor. If you remember, we start our devices with the p-n junction, the normal, the simple p-n junction, dealing with the p region and region, or what we call it, the electronic dot. Then we go to the metal oxide semiconductor field effect transistor, or what's abbreviated by FET or MOSFET. In the MOSFET, I mentioned twice that MOSFETs are unipolar devices. I mean, the carrier transport or the electrical current conducted in the MOSFET is due to the movement of the electrons or the movement of holes. When we are talking about an N-channel MOSFET, then the electrons are the source of electrical current. And when we are talking about the P-channel MOSFET, then the holes are the source of an electrical current. Now, as you can see from the title, our device today is a bipolar device. I mean, the current conducted in this device will be due to both electrons and holes. So let's start together the journey for the bipolar junction transistor. Okay, as usual, we will start the journey with the schematic. Our bipolar junction transistors include or consist of three main regions. Two similar regions in the right-hand side and the left-hand side, and what I mean by similar is they are of the same type of doping. So here we have an N region on the left side, what we will call it the emitter, and we have an N region on the right side, what we will call it collector. And in between we have what's called the base, which is a P-type region. Similarly or complementary, we can have another device which is P-N-P device. So BJT can be either an NBN configuration or a PNP configuration. During this lecture, my dear students, we will focus our study on the NPN transistor. However, following the same procedure and by some sort of analogy, you can apply the same theory on the PNP transistor. So let's start with this journey. If you remember, my dear student, we already investigated a similar energy band when we start considering together the cross-sectional energy band for the source, channel, and drain in the MOSFET, if you remember. So let me, for a while, return to my whiteboard. Okay, so I think now you can see my whiteboard. Let's stop sharing. So, okay, that's perfect. So, if you remember the MOSFET schematic, it looks like that. For example, if it's an N-channel MOSFET, so this is the source, and this is the drain, and in between we have what's called the gate side, and then here is the gate metal, and this is the channel, and this is a bit substrate. And whenever we start the MOSFET, we start with this energy band diagram by making a cross-sectional cut here and plotting this energy band diagram, which is an NPN junction. Now, in our BJT device, which looks like that, here is the N, here is P, and here is N. This is called emitter, and this is called base, and this is called collector. And then when you are going to make an energy band diagram, you will have typically the same energy band diagram, which is still an NPN energy band diagram. So this is one common point between the MOSFETs and the BJT. Now, let's turn again to the PowerPoint presentation, please. Okay, and again, let's open our laser pointer. So this is a circuit schematic for the BJT. This is the base, this is the collector, and this is the emitter. So this shape or this schematic for the transistor, we will do a lot of exercises about it in your next semester course, in the electronics 1 course. So it will be a full circuits course. But let's now return back to the physics as a semiconductor here. So this is the schematic. Of course, this is the complementary device. I just mentioned it. This is a PNP device, which is the complementary device. I'm sorry. So this is the NPN, and this is the PNP device. And let's do the energy band diagram. So this is the energy band diagram. I believe this is what you see previously. Maybe there is one thing missing here in this energy band diagram, which is the Fermi level. So let's go together and plot this Fermi level together. As far as this device is under thermodynamic equilibrium, so we can plot a Fermi level like that. Okay, so this is the Fermi level. As you can see, okay, I'll return back to my laser pointer. Okay, perfect. So as you can see here, this left-hand side region is an N region because the Fermi level is more close to the conduction band. Similarly, for the right-hand side region, it's an R region. So here we have an excess electrons, or the electrons are the majority carriers. Similarly here. So if you now, this is the emitter and this is the collector. Maybe later on we will know why we call this an emitter and why we call this a collector. And in between we have the P-type region. So here we have excess holes. All the holes is the majority carriers in the in-between region. So this is the thermodynamic equilibrium because I plot the Fermi level and horizontal line. So simply this is a thermodynamic equilibrium condition. And under thermodynamic equilibrium, no majority carriers will be able to move because simply electrons here will find this barrier. So electrons will not be able to move to the right. Similarly, the electrons here will not be able to move to the left due to this barrier. And in between, this hole is bounded because, as you know, the energy of holes increase by going downward. So these holes these holes are bounded between this barrier on the left and this barrier on the right. So at thermodynamic equilibrium, no current will move, which is something actually obvious because you don't apply any type of voltage. Now, what we are going to do is to examine together what if we start to apply voltage. And in order to examine this, let's make it in a very simple manner. Actually, this schematic diagram is simply can be treated as two p-n junctions. So this is a p-n junction or an NP junction, and this is a p-n junction. Each junction, as you know from your previous lecture, that each junction can be either a forward bias or a reverse bias. If the junction is a forward bias, then this barrier will be alternated to be a drift. If this junction is a reverse bias, then this barrier will increase. Very simple like that. So what we are going to do in the remaining part of the lecture is simply we will ask ourselves, does this junction is a reverse or a forward? And please remember that we have two junctions. We have the emitter-based junction and we have the base collector junction. So simply what we are going to do is that we will going to examine the condition of these two junctions. Either they are in the reverse bias or they are in a forward bias. Okay, let's just start doing this. So let's start with the first one. As you can see from the schematic diagram here, now we are considering this junction, which is the base collector junction, because now your battery is connected between the collector, which is this one, and the base, which is this one. So you are now considering the base collector junction, and nothing is applied on the emitter base junction. Okay, now as you can see from this configuration that the negative terminal of the battery is connected to the P side, which is the base, and the positive terminal of the battery is connected to the N side, which is the collector. So again, from your previous lecture, if you remember, whenever you are connecting a negative voltage to the P and the positive voltage to the N, then this device is under reverse bias. So whenever you have a PN junction in the reverse bias, then what will happen is simply that this barrier will going to increase because you are in the reverse bias. So this is typically what happened here. This barrier is going to increase because you apply a negative bias or a reverse bias to this PN junction. And again, nothing have been changed here because nothing is applied. There is no voltage applied to the emitter, so this PN junction is neutral. Now, as you can see, if you have an electron here, these electrons will automatically drift in a very high speed to this side. But the question now is, do we have electrons here? Typically, the answer is yes. We have electrons here, but these electrons is a minority carriers because this is a p side or a b doped region. So the electrons in this region is considered as a minority carrier. Accordingly, no current still moving due to the majority. Again, what will happen is just a few amount of a minority carrier will drift from this B region or the base to this N region or the collector, but nothing will happen to the majority. Still this holes are bounded. And let me also remove this red line because now this red line has no meaning. So this holes is still bounded. This electrons still see this barrier, and this electrons still this a huge barrier. So nothing will happen. However, but what if we connect another battery here? So still this is in reverse bias, but now we connect another battery here. This battery now is connected so that the positive is toward the base and the negative is toward the N or the N region. The positive is toward the P region, which is the base. The negative is toward the N region, which is the emitter. So this emitter base junction is a forward junction. Again, let's turn to our previous lecture. Whenever we have a forward junction, then whenever we have a forward junction, then this barrier disappears and the electron starts to move. So after applying this junction to be a forward junction, what will happen is simply that electron will move from the emitter to the base because now this emitter base junction is forward. But let's now check. Whenever the electron reaches the base, it will find a huge drift. So electrons will move very, very quickly in a very high speed to reach the collector. So as you can see, this is the emitter because this is the place where we emit the electron. And this is the collector because this is the place where we collect the electron. And in between, this is the base. This is the valve. Whenever we destroy the barrier in the valve, electrons will start to move. But also, please don't forget that as far as you put this junction as a forward bias, also hole here, which is a majority in the P region, will start to move in this direction. Because simply this is a forward bias junction. So holes will start to move in the left-hand side direction. That's why this device, my dear students, is called a bipolar junction transistor. This is simply because current now is flowing due to electrons coming from the emitter, passing to the base, reaching the collector, and also due to the current due to holes in the base which travel to the emitter and conduct current. By the way, we also have holes here which will drift to the base and then to the collector and then sorry to the emitter, but these holes is a minority carrier, so its contribution is minimal. So current is flowing from the emitter through the base to the collector, and also its current is flowing from the base to the emitter. So the current in the emitter is due to both electron traveling from the emitter to the collector and also holes traveling from the base to the emitter. We will call this configuration in the active mode configuration. What do we mean by active mode is that in this mode, the transistor is conducting current due to its majority carrier, as you can see. And the sign for the active mode is to have this base collector junction, to have this junction as a reverse junction, and to have this base emitter junction as a forward junction. So whenever you have this configuration, I mean the emitter base is a forward and the base collector is a reverse, then you have the active mode of the transistor. Okay, so what are the problems that may face such a device? As you can see here, these electrons is traveling from the collector to the, from the emitter to the collector through the base. And as we discussed together, this base is a p-type region. I mean, it includes a huge number of holes. So there is a probability of what's called a recombination. A recombination simply is as follows. We have an electron traveling from the emitter to the base to the collector through the base. When this electron reaches the base, it finds a hole. So this electron lose energy and return back to the valency band to recombine with one of these holes. So now you lose this electron from the journey because this electron will recombine to the valency band and it will not reach the collector. That's why we call this the recombination process. So the recombination process is simply the process of returning the electron back from the conduction band to the valency band to recombine back with an hole. Of course, this is an unwanted phenomenon because simply when you have, for example, 100 electrons traveling from the emitter to the collector, if 50 of them recombine here, then you lose 50% of your current. So how should we solve such a problem? Or what is the ways in order to solve such a problem? Actually, we have two solutions. The first solution is to make this base dimension very narrow with respect to the emitter and the base. Sorry, and with respect to the emitter and the collector. So this distance is very short. As far as you shorten this distance, the probability of recombination decrease. So the first way in order to avoid, or let's avoid, in order to minimize recombination is simply to shorten the base distance. That's why you're decreasing the probability for recombination. Another way to reduce the recombination is to increase the doping of the emitter with respect to the base and collector, because simply the emitter is the source of electrons. So you need to increase the number of electrons who are traveling from the emitter to the collector. So this can simply happen by increasing the doping, because you know that whenever you increase the doping, you increase the number of free electrons, whenever it's an N doping. So that's why we use this plus sign in the superscript of N to indicate that this doping is much higher than the doping in the base and the doping in the collector. So these are the two ways where you can decrease or limit or minimize the recombination effect in a BJT or in a bipolar junction transistor. Now, this is the IV curve. As you can see, my dear students, this IV curve looks similarly, much similarly to the MOSFET, if you remember. We have a region where the current and voltage are almost linear. We call this region a saturation region here. And we have the active mode region, which the one I mentioned here. Whenever you have this junction is a forward, and this junction is a forward, and this junction in a reverse. During this lecture, actually, we will limit our focus on the active region. But typically, you can understand that whenever we are considering the BJT as it consists of two diodes, then we are typically have four conditions. One of these conditions is the active region condition, where we have one junction, which is the emitter base junction is a forward, and the collector base junction is a reverse. This is the active region, which is represented here in this curve. And we have another four regions. Whenever both are reverse, this is one region, we call it cutoff. Whenever the emitter base is reverse and the collector base is a forward, and we call this as reverse active, and this is actually will not be considered anyway in any course. And the third one, which is and also the fourth one, which is the saturation, whenever we have both of them forward. Maybe in the next semester, inshallah, in the electronics course, we will go more deeply toward understanding the saturation and the cutoff, but during this course, we will limit our understanding to the forward or the active forward mode, which is one junction forward and the second is reverse. Finally, in this lecture, we will going to understand what's called the Eber-Mole model. It's actually a very simple model because we just mentioned it. We are considering now this bipolar junction transistor as two diodes. Here is the emitter, and here is the collector, and here is the base. This is the first BN junction. This is the first BN junction, which is the first diode, and this is the second BN junction, which is the second diode. So this is simply how we can model the transistor. We have two voltage. We have the voltage between the base and the emitter, which controlling this junction, and we have the voltage between the base and the collector, which is controlling the second portion or the second junction. So this is simply the Eber-Mole model. During the next course, inshallah, we are going to understand more and more about the current flowing here and there. This is actually very simple model because this equation, I believe we already see this equation if you remember in the diode lecture. So this is the equation for the base emitter junction, and this is the equation for the base collector junction. So what we are going to do is that we are going to combine these together into a one big model, including these two PN junction, and this is typically the energy band diagram you just see some slides ago. So this is typically what we are going to do in the next semester, inshallah. In the next semester, we are going to understand this model, which is the Eber-Mole model or the EM model, and then we are going to, this is actually another circuit model for it, and then we are going to study these current curves and these different modes. So this will be a part of our next semester module, inshallah. This is actually, as I mentioned, a short and a very short actually journey with the BJT. Maybe in the next semester, inshallah, we will have more time. Maybe we will have something like a 2 to 3 lectures in order to cover the BJT from a circuit perspective. What we understand now is just the physical model of the bipolar junction transistor. So thank you very much for your concentration, and see you in the final lecture, which is the tunneling field effect transistors. Thank you very much, and see you later on in the next week, which will be, inshallah, the terminating week for this module. Thank you very much.